Hello, my name is Nolan Johnson.
My name is David Valdez.
Hi, my name is Stephen Ha.
Hello, my name is Everett Gioco, and my role for this project was the CAD modeling and fabrication.
I was mainly tasked in this project to do the coding aspect, making sure our front end, back end, broker, and Pico were all connected, as well as doing the AI code to make sure we could send the ESP32 camera image to ChatGPT through an API call.
Throughout this project, I helped determine what resistor was most recommended to use throughout the circuit. I was also able to create each circuit for the sensor, as well as uploading files to and from the Pico, and as well as uploading files into the camera. I was also able to help assemble the cast for our gadget, as well as testing the sensors if they work properly or not.
I was responsible for the calculations, setting up and wiring the hardware, coding the sensors, and testing and calibrating our gadget. Initial design approach. So our main goals were to have a spacious interior and a hard exterior. A spacious gadget allows us to make changes without having to worry about whether it'll fit or not, and a hard shell would prevent any damages or disconnections inside. We first thought about making a walking boot, however the constant pressure on the bottom makes it more susceptible to damage, and its limited vertical movement prevents the sensors from taking readings in higher places. We shifted to our final idea, which was an arm cast. This would allow for much more flexibility and is more protective.
For the mechanical design, we chose to laser cut nearly all components, instead of 3D printing, which saved time and ensured better precision. The structure was fully modeled in SolidWorks using two-dimensional profiles designed to be press-fit together. After testing the assembly in SolidWorks for fit and alignment, we moved straight to fabrication and built the final structure.
Electrical schematics. So in this image, you have the image of our circuit, and what is happening here is the Pico is powering each sensor and is connected to each sensor by a GPIO pin. The camera itself has its own code uploaded through a website that we use called Arduino IDE, and each GPIO allows the Pico to send code to and from the sensor. On the bottom right, we have an image of our circuit, which essentially is our voltage regulator. Unfortunately, couldn't use it, and because we couldn't output the right voltage, but that was essentially our plan.
So now we will talk about the CS side of things. So there were 4 values that we had to utilize our sensors for to get measurements. This included light, which we needed in lumens, temperature in Fahrenheit, humidity in percentage, and distance in centimeters. And this was the code that we used to upload to the Pico to be able to get the values back so that we could send to their website. So light, we are simply just using some calibration values, using our conversion formula and getting lumens back. Temperature, converting to Fahrenheit and returning that. And humidity, we just kind of utilized the built-in sensor for that. And then distance, we also had to use some code, convert to centimeters so that we would get the right values back. So we also had to utilize the ESP32 cam to be able to send the picture to ChatGPT utilizing a API call through OpenAI. So this receive.py code here would download the image from the ESP32 cam, and then we would then send that to process image function, which was in the send to OpenAI code. And in the send to OpenAI code, we would get the image, then we would send that to ChatGPT. We would get a text response back, but then we would convert that text response to a audio file, and we would send that to our front end so that we could utilize that on our website. And this is kind of what the styling of our website looked like with nothing plugged into it. We can see that the key features here are that it is able to display the real-time sensor readings, which I'll show later, but you can see that they will show up here. There's also the send message to Pico option here, allowing the users to easily be able to communicate to the OLED device in very little time. And there is the camera control here, where if you click take picture button, after a few seconds you'll get the most recent pictures shown on the website here. Additionally, you will also get a seek bar with the volume slider that will show what the AI had to say about your image. And so now I'll showcase two quick demo videos showing kind of how our website was able to function and communicate with the gadget.
Kevin?
No,
500?
31,570.
570, okay.
Yes, there you go.
Do we have a
Okay.
number?
Okay.
Do we have
31,570.
So you can see there that we are very quickly able to type the message out on our front end, and then that would communicate to all the way to the Pico, which would then show it on the OLED device, and the agent was able to see that very quickly. The second image here showcases, well, first we can see the sensor readings. We can see that these are getting showcased on the front end from the Pico. And additionally, we were able to click the take picture button. This would show the most recent picture taken by the ESP32 cam, embed that into the front end, and additionally we would also get the matching AI description describing the image.
There is a large framed picture or poster. The artwork in the frame appears to be a reproduction of Claude Monet's.
So we were able to see that the AI was correctly able to determine the artist of the painting, Claude Monet.
So overall, this was actually a very challenging project, but one of our main concerns was just effectively communicating with a person with unstable Wi-Fi connection from the school, and another one was getting a power source to output 5 volts, as well as diagnosing circuits or just code itself, trying to find out what the problem was or what was disconnected. So following the engineering design process of customizing and decustomizing, we were actually able to get what we actually desired. Getting all the sensors to work was our main priority, but for the most part, we actually couldn't get the voltage power supply to get running since the voltage regulator couldn't start. And we also had to change the photoresistor from location from the side to the top to get more proper data. And another thing was we were actually able to get the OLED to send one word, as we originally thought, to actually multiple phrases and sentences.
I handled most of the fabrication for the final design. We aimed to imitate the look and feel of an arm cast with all electronics embedded discreetly. I used laser cutting for the main structure along with hot glue for quick assembly, minimal stitching for support, and a lot of soldering to connect the internal components. The camera and ultrasonic sensor were mounted at the front, while the rest of the sensors were hidden throughout to keep it clean and wearable.
modifications? The first modification we like to make is to improve the internal wiring and attach loose components. This would prevent any wires from stabbing the wearer and any disconnections. Building off of that, part of our initial design was to have a hidden pocket containing the OLED that would be lifted up by a servo whenever a message was sent to it. However, we were unable to implement this feature and the OLED remains loose. The next modification we'd like to make is to 3D print an actual cast cover similar to the image shown. This would improve the durability and aesthetics of the cast. An idea we had was to have all the mentors sign the cast, which would have been a cool way to thank them for helping us. The last modification would be to fix the battery circuit and get it working instead of having to use the external power bank. Things to do differently. The main thing we do differently is to prepare better before the hack. This includes being more proficient with Python and knowing how all of the hardware works. Another lesson we learned was to be more time efficient. Troubleshooting took up way more time than we expected, and that caused us to fall behind. The last thing is to make sure everything is fully functional before soldering and hot gluing everything onto the gadget. Although it's not permanent, fixing it could be a very time-consuming process.
We learned early on that thorough testing was critical, so we used breadboards and offline setups to debug circuits and code before full integration. Dividing the work based on each team member's strengths helped us move faster and avoid bottlenecks. And with the tight deadlines, time management became essential. We had to prioritize and stay flexible even during 10-hour workdays.